Here we are on the final lesson on solving, on the matrix unit, but we're going to be solving systems of linear equations using matrices. The first way we're going to do it is something that sort of the lower level skill using a calculator, but we're going to use the inverse matrix like I taught last class when we take this equation, the matrix A times some unknown matrix X equals matrix B, and we do left-hand matrix multiplication of A inverse on each, and we get that matrix X equals A inverse B. So the difference between what we did last class and this class is that now I'm not giving you the matrices, I'm giving you a system of equations, and you have to write that system as a system of matrices. So let's go ahead and try that. We basically are going to write a 3 by 3 matrix because we have 3 equations with 3 variables, and I write the coefficients in. Coefficient of x, y, and z are all 1. Next coefficients of x is 5, then -1, then there's no z, so 0. So 5, -1, and 0. Then here 3, 4, and 1. And then here we have the x that we're looking to solve for, and then the B matrix is going to be a 3 by 1 with just the coefficients, 10, 1, and 8. I should say the constants, not the coefficients. So this is me setting up the system of matrices that we're going to solve. This is taking the A times X equals B and doing left-hand multiplication on both sides. And of course, when we multiply inverses, we get the identity matrix, so that goes away. We're left with X equals A inverse times B. So in order to solve for that, what we're going to do is pull out our calculators, and we will go ahead and plug both of those matrices into the calculator. Okay, so I pulled up my calculator and I input my first matrix as just the coefficient matrix, the 3 by 3 that we determined. Now I'm going to go back to second matrix, go over to the edit screen again, go to the second matrix, and this time I'm going to put in a 3 by 1. Remember, it's row by column. 3 rows, 1 column, and then I'm going to do 10, 1, and 8 as these are the constants on the right side of the equation. And to solve, I call up the first matrix A, I take the inverse of it, and I multiply by the second matrix B, and I get my solution matrix. And this is a lot of decimals. I think I can do math frac. I choose math, and then choice 1 is frac, and I can put my answer in fraction form. So that's a better way to write with matrix. We typically don't use decimals. We'll use the fractions. So that would be your solution here. So the next couple of questions on the lesson ask us to practice this. So I'll go ahead and help you set up the matrices, and then I'll let you do the calculator work. So I know I need, these are both systems that are 3 equations and 3 variables. So I'm taking the coefficients of -3, -2, and 4, the coefficients of 0 for x, 3 for y, and -2 for z, and then 4, -3, 2. And then the constants on the right are 9, 5, and 7. So you're going to make sure you put this in for the A matrix and this in for the B matrix, and then you'll take A inverse times B, and the resultant matrix that you'll get, the solution matrix, will be the X matrix. It's going to be the matrix 3, 7, 8. The next one, we're going to go ahead and set up a 3 by 3 matrix again, the X matrix that we're solving for, and then a 3 by 1 matrix will be our B matrix. So the coefficients here are 1, 2, and -1, then -2, 4, and -1, then 2, 2, and 3. The constants are -4, 6, and 1. And remember, this is my A matrix, this is my B matrix, and I take A inverse B, and I will get my solution matrix, A inverse B. My solution matrix will be -3, 1/2, and 2. So check that work on your calculator to make sure that you are getting the same thing, to make sure you're using your calculator correctly here. So the real reason why we're doing matrices in this unit is to get to the point where we can learn about Gaussian elimination. So Gaussian elimination is a way to solve this system of equations using row operations, elementary row operations that we learned in the last lesson, which are when we swap rows, we can multiply a row by a constant. We can multiply a row by a constant and then add to another row. We did a variety of matrix operations last class. And the goal is to put the matrix in reduced row echelon form. We're going to do that today, but we're going to use it to actually solve a matrix. So the first thing I have to do is introduce you to the concept of an augmented matrix. So an augmented matrix, instead of writing two matrices, one of the coefficients of the variables and another one of the constants, we're going to write a single matrix called an augmented matrix where we have the first entries are the coefficients of the matrix. So I'm just using this matrix, using this system of equations and pulling the coefficients. Let's see, 0y here and -2. And then I write a vertical line in here, and on the right side of the vertical line, I put my constants from the right side of the equation. This is called an augmented matrix, where we have the original coefficients on the left in a 3x3, and then we have the constants from the right side of the equations to the right of this vertical line. Now what we want to do is get this to reduced row echelon form where we have ones along the main diagonal and zeros all the way over here to the left. So the nice thing is we already start with a 1 here, we already start with a 0 here, and we already start with a 1 here. We already have a 0 here. Looks like I really need to work on row 3. So the first thing I'm going to do on row 3 is to take row 1 and add it to row 3 and then replace row 3. So remember, when my arrow points to row 3, that is the only thing that I'm changing, which means row 1, including the augmented side, doesn't change. Row 2, including the augmented side, doesn't change. And then for row 3, I'm adding row 1 to row 3, so 1 plus -1, and placing that in row 3, so 0. Then I have 1 plus 0 gets me 1. -1 plus -2 is -3. And you're also performing the same operation on the augmented side, so 9 plus 2 is 11. So now it looks like we need to eradicate this 1 right here, make it a 0. So I'm going to go ahead and multiply row 2 by -1 and add that to row 3 and replace row 3. So here's my operation. Remember, I'm only impacting row 3, so I only need to worry about changing row 3. So I'll keep the same first 2 rows that I had in my matrix above. And then for row 3, I'll take a negation of row 2 and add it to row 3. So I'll still get 0 plus 0 is 0. Then -1 plus 1 is 0. -3 plus -3 is -6. -3 plus 11 is 8. So I'm doing a lot better here. I now just need to make this into a 1. So the best way to do that is just to go ahead and multiply it by -6. And then I'll row replace row 3. So in this whole process, I'm only working on row 3 because my first 2 rows were already in reduced row echelon form, which is a nice, easy way to start this. So now I'm taking my -6, multiplying by -1/6 to get a 1 here, and then 8 times -1/6 will get me a -4/3. So I'm now in reduced row echelon form, and I'm going to come over here. I'm going to go ahead and bring over the augmented matrix in reduced row echelon form so I can work with it. So I have 1, 1, -1, and then on the right side of the vertical line, a 9, and then 0, 1, 3, and then a 3, and then a 0, 0, 1, and a -4/3. So now I can write a system of equations from this with these coefficients. This will be 1x plus 1y minus z. So x plus y, minus z equals 9. Then I have 1y plus 3z equals 3. So y plus 3z equals z. And then I have just 1z equals -4/3. So guess what? -4/3 is my z value. I'm going to write that up here. So I've solved for one of my 3 variables. Well, now that I've solved for z, I can plug that into this z right here. So y plus 3 times -4/3 equals 3. This was a 3 right here that didn't write very well. So this is y minus 4 equals 3. So now I know that y equals 7. I can write that solution up here. And then now I can sub in both my y and my z into my original equation, my first equation, I should say. So x plus 7 minus a negative 4/3 is plus 4/3 equals 9. I'm going to go ahead and subtract 7 from both sides. So I'll get x plus 4/3 equals 2. And then I'll subtract 4/3 from each side, and I get x equals, let's see, that will give me 2/3. And that is my final answer. And I have now solved that system of equations they gave me using the work to get to reduced row echelon form via Gaussian elimination.